Hello there. Today we'll look at GLIDE towards photorealistic image generation and editing with text-guided diffusion models by Alex Nicol, Prafulla Dhariwal, Aditya Ramesh, and others of OpenAI. This paper on a high level, well, I'll just show you what you can do. I'm sure you've all seen this paper in one way or another. It is another paper that generates images given a piece of text. But this time it's not a GAN or anything like this or a VQ-VAE. This time it is a diffusion model. This is a different class of models, and we'll go into what they are and how they work. But essentially, you can see right here that the model that turns out of this, and of course, this being OpenAI, they trained this on a massive scale, and this model is really big, but what comes out of it is very, very, very much better than, for example, DALL-E, which always had this kind of blurriness to it. You can see right here a crayon drawing of a space elevator, pixel art corgi pizza. So this is trained on a big scrape of images from the internet, and as you can see, the outputs are pretty stunning. So it gets, for example, the shadows right here, it gets them correctly, even the red on blue blending. It gets different styles, like the Salvador Dali style. It combines different concepts, although maybe, this has been seen on the internet somewhere, but it is able to combine different concepts. And given that these are diffusion models, you can actually do a bunch of more stuff with them. For example, inpainting is immediately accessible to this model. Now, usually inpainting is accessible to diffusion models. However, they actually train an inpainting model on top of this. But in essence, a lot of stuff would be accessible. So this is now possible where you say, okay, I only want to change a part of the image, like this part right here. You give a text saying a man wearing a white hat, and the model generates the man wearing a white hat. This is very cool. You can do things like this where you first, so the pictures here are a bit confusing, but you first generate an image from a text prompt, like a cozy living room. Then you get this living room, and then here the user would annotate this window, sort of would draw over it, and would give the next text prompt. And the next text prompt would be a painting of a corgi on the wall above the couch. And the model, so this is the inpainting mode. The model would only be able to paint the green area, so it would sort of try to conform to the text using only the green area, and therefore it would make this corgi picture on the wall right here. Then the user goes further and says, well, now I'm going to paint this area right here, and I'm going to issue the prompt around coffee table in front of a couch, and the model will generate it, and so on. You can see that this enables sort of an interactive creation of this scenery. At the end, the couch in the corner of the room, so changing the entire wall right here. You can see the back of the room has some space, and now it's being changed to a wall. So this is the kind of stuff that's possible. Editing right here. Even what's this sort of sketch editing where you don't only mask, but along with the mask, you provide sort of like a sketch, as you can see right here. So this part here is blue, and then the part here is white, and that's also the mask that the picture receives. And you can see that only one cloud in the sky today. It's sort of, you can guide even more. So you can guide with text, and you can guide with sketch color, and so on. So this is a very, very, very cool model. You can see the quality is very, very good. Here is, for example, a comparison. These are real images from the MS Coco dataset, sorry. This is a dataset of pictures with associated labels, so text descriptions of the picture. So you have some ground truth. So the ground truth here would be this one, and the label is a green train coming down the tracks. You can see DALL-E generates something neat, but it's sort of blurry. It's kind of cartoonish, as all the DALL-E pictures are if you look in this row. The last one's pretty good, but all the other ones are sort of, elephants are more like blobs. And we've seen this in the DALL-E paper. It was impressive at the time, but this is way more impressive. And then their best model, this glide model with classifier-free guidance, you can see right here, it generates like a high quality train that fits the image description. And you can see in the entire row right here, it's pretty good at doing that. So there are a lot of components to this model, and we're going to explore them a little bit. OpenAI has released, in classic OpenAI fashion, they've released like a small, very filtered version of that model because they're worried about safety. Like anyone's going to believe them after GPT-2. They've just been doing this every single model, right? They're just like, oh no, safety. People can make deep fakes. Oh no. Like, no one's made a deep fake. Like, GPT-2, all the worries, they were just not true. No one has used GPT-2 to spread around fake news. And no one's going to use this model substantially to make very misleading pictures. But we'll get to that as well. All right, so what is a diffusion model? And that's sort of at the core of this thing right here. A diffusion model is a different type of generative model than maybe you're used to from like a GAN or a VQVAE. So in a GAN is probably the closest right here. So a GAN is sort of like a neural network with a bunch of layers. And what you do is you sample from some sort of a distribution. You sample some noise, right? You sample some noise, you get some noise vector. So here's a vector with just complete noise. Every entry is noise. You put it through the network generates pretty picture. And you train the model using a discriminator in this case. You train the model to produce pretty pictures given the noise. And the noise acts sort of as a source of randomness. So the mapping is clear. You train to map from noise to picture. Now, a diffusion model goes in almost like a different direction. So what you do is during training, you have a data set and you take an image. So from a data set, you have a data set, you take an image out of it. Let's say this is your trusty cat, and you're going to put noise onto this image. So you're going to add noise, and noise, let's represent that with sigma. No, I think they do epsilon or eta in this paper right here. So you add that, and then you get a slightly noisy version of this. Let's just wiggle a bit. Wiggle, wiggle, wiggle. And you do it again. So through adding noise, and you add lots and lots and lots of noise, okay? So every time you add a tiny, tiny bit of noise, and that means that more and more your picture is just going to be blurry and blurry and blurry. Now, if you do this for long enough, in the limit, you can prove that obviously if you do this infinitely many times, what comes out at the end is going to be just normally distributed. If your noise is normally distributed and you scale every time correctly, then whatever turns out is going to be normally distributed with some parameters here. So this right here is going to be a known distribution. If you add noise for long enough, if you destroy all of the information that the picture has, then you'll end up with sort of an entry in a known distribution. However, every step that you do right here is very small. Every step, you just add a little bit of noise. So technically, it's possible for a model to look at this picture right here, which is kind of a bit of a blurry version of the cat, and predict and learn to predict the more sharp version of the cat. Okay, this is a foundation of many sort of denoising models, many upsampling models, super resolution models, what have you. Okay, they do this in one step, but essentially here we say the individual step is small enough such that the model can technically learn to reconstruct it. However, if we do it for long enough, in going to infinity, we are at a known distribution, namely the standard normal distribution. And these two things together mean that Well, if we have trained the model to reconstruct the individual steps, what we can technically do is we can now go ahead, sample from this known distribution, right? Because ultimately we want to sample from the data distribution, but that's hard because we don't know it. But here we can just sample some noise from a known distribution, then put it through this process of reconstruction all the way, all the steps that we did up here during training. During training, we just noised and noised and noised the images again and again and again. We trained the neural network to for every step to reconstruct the previous step. So we can now just put it through this series of trained neural networks. In fact, it's just going to be one neural network that gets the index of the step as a parameter, and out comes an image, right? Out comes a true data image. If these two things up here hold, then this should be possible. This is the basis for these diffusion models. So specifically, given a sample, that's what they say here, given a sample from the data distribution, this is x0, so this is the data distribution, we produce a Markov chain of latent variables x1 to xt, with everyone being a more noisy version, and xt finally being of a known distribution, because we do it infinitely or a large number of times, by progressively adding Gaussian noise to the sample. So you can see right here, we take xt minus 1, we scale it down a bit, because if you wouldn't do that, the image would just increase in scale over, because we just keep adding stuff. But it's just a rescaling. There's nothing more happening here. So we add noise. This here is the mean of a distribution. The covariance matrix here is a diagonal, which essentially means we just add a bit of noise of the scale of alpha t. No, sorry. We just add a bit of noise. We rescale by alpha t, which is a scaling factor. And that's how we obtain the next step, the xt. So again, we do this enough. So we take xt. For the next step, we plug it in here. And then we obtain xt plus 1, and so on. So if the magnitude of the noise added at each step is small enough, the posterior is well approximated by a diagonal Gaussian. That's what they say right here. So what does this mean? The posterior, it means that this is the reverse step, right? I have xt, and I'm looking to recreate xt minus 1. So if the noise is small enough, then the posterior is well approximated by a diagonal Gaussian, and we have a hope to learn it with a neural network, right? Furthermore, if the magnitude of the total noise added throughout the chain is large enough, then the last step is well approximated by a standard normal distribution. These properties suggest learning a model for this posterior, right? We have xt, we want to reconstruct xt minus 1 to approximate the true posterior. Okay, so we are going to learn a neural network that it doesn't exactly reconstruct the image, but this is a variational model. So what we're going to do is we're going to plug in xt into a neural network. The neural network is going to predict the mean and the covariance matrix of the next step up the chain, of the next step of the denoising chain. And then we can use this to produce samples. We simply, we start with Gaussian noise, which is the end, and we gradually reduce the noise in a sequence of steps until we are at the data distribution, or at least the predicted data distribution. So this is not a new idea. This has been, and I think I have the references open, this has been explored previously. For example, this is just an example right here. Denoising diffusion probabilistic models is one of the papers that introduced lots of these things. You can see right here. These have still been trained on just images as such. So this is, the left is trained on a face data set, the right is trained on CFAR10. This is unconditional generation without a text prompt or anything like this. But you can see the same principle applies. We simply add noise during training, and we learn a neural network to remove the noise, to predict what the image would look like one noise step less. Here already, there was an invention that the paper here would make use of, namely the loss function right here. We're going to look at that in just a second. Oh, that's the second. So they say, while there exists a tractable variational lower bound, better results arise from optimizing a surrogate objective, which reweighs the term in the variational lower bound. So the loss we're going to optimize right here is during training. If you can see right here, during training, we train the neural network to reconstruct one of these steps, right? Each sample in training is going to be some image xt minus 1 and some image xt, and we're going to train the neural network to predict xt minus 1 from xt, or the variational sort of the distribution of that. So this is a training sample. Now, how do we get the training sample? What we can do is we can take x0 right here, and we could go through and add noise, but since we always add Gaussian noise, we can simply do this in one step. There's nothing depending intermediately right here. So we do it in one step right here, and then we add another bit of noise. That's how we get the two samples. And then rather than predicting the image itself, what these models do is they will predict the noise. So what we actually predict is going to be the noise epsilon here, which we can calculate by xt minus 1. So this is our prediction target. This is our loss function. The network is supposed to output this right here. And of course, we know the true one. You can see the network will try to output this given xt and an index into which step it is. So we're going to tell the network, by the way, here's the noise, here's the number of steps we're into this process, and we're going to train the network to say what was the noise that was added. It's a bit easier. I think it's just like a scaling property, because this is going to have sort of zero mean and unit variance. So it's easier to predict for a neural network. So that is very standard in diffusion models. The next thing they introduce is guided diffusion. By the way, they also mention somewhere that they learn the covariance matrix. Yes, there's another paper that also learns the covariance matrix. This first paper just fixed it at a diagonal, but then there is another paper that improved upon that, called Improved Denoising Diffusion Probabilistic Model, interestingly by the same authors here, and they show a method to learn this covariance matrix, which is mostly a scaling issue, because there's a narrow band that is a valid covariance matrix, and they show with the correct parameterization, they can in fact learn it and get better performance. But this is just for reference. It's not super important right here. The second part is more important. So this is guided diffusion. So what we can do here is we can build a model. Let's just assume we have images and we have class labels for the images. Let's leave away the text right now. Okay. So we have a class label for here. So this has a class label of cat, for example. There's also dog and so on. So what we can do is we can train the neural network here. Each step we train it to reconstruct one step. So that's going to predict the noise that was added given the image xt, given the index t. And what we can also do is we can say, by the way, we give it the label y. So y in this case is cat. So we can train a class conditional model, and that has some advantages. We know class conditional GANs work quite well. So if you give it the class label as an input, you can often improve that, and you would do that by either embedding the class label as a one-hot vector into the network or something like this. Now with the text model, it's a bit more tricky, right? But what you can do is let's say this here is some sort of a neural network, right? So xt goes in, this is xt, goes into an encoder with a bunch of layers. Maybe the T itself also goes in here as some sort of a float or an embedding, a one-hot vector or something like this. And the class label could also go in here, right? However, if you have text, what you can do is, let's say you don't have this, but now you have a text description. They call this C. So you can first put the text description through its own network and then combine the embeddings. So either put the embeddings here as sort of a class embedding, or you can put the embeddings into each layer right here in this stack. And I think they do both. In any case, you can embed the text right here of the image, because their dataset always has images and text together. So that's what I said at the beginning. So you can take this text, you can put it through an encoder itself, you can input it into this process right here. This is the network that is going to ultimately predict the added noise given an image. And yeah, the network can take inspiration, can learn from the text. So if it sees this picture right here, for example, but in a very noisy way, and it has the text information, a couch in the corner of a room, it's obviously going to perform better than if it wouldn't have the text. And ultimately, that's going to unlock the capability that we can input a text at the very beginning, and then the model guided by this text will produce a living room, a couch in the corner of a room. So now, is this enough? And the answer is not yet. So class conditional models are working fine. However, it's better if you do what's called guided diffusion. So in guided diffusion, we not only want to make our models class conditional, but we want to guide them even more. We want to push them into a direction. And this is called guided diffusion. And one way to do it is to say, well, I have an additional classifier. I have a classifier, for example, an ImageNet classifier, right? And if I want to push my diffusion process towards a particular label, I can take that ImageNet classifier and I can go along the gradient of that. This is very much like things like deep dream work, or this is essentially clip guided diffusion is this, but with clip. So I have the clip model. And if you don't know what the clip model is, this is a model where you input an image and a piece of text, and it tells you how good do the, so let's put that as sigmoid, do these two things fit together well or not? Now, if you think about the gradient of this with respect to the image, then you can see that you can push the diffusion process into a direction where the image would fit together with the text more, because you go along the gradient of that. It's kind of, you construct an adversarial example towards this classifier. So this is one way of doing it, but it means that you have to have some sort of an external classifier to go by. There is also a method called classifier-free guidance, and this was introduced by Hohen Solomons. And this is where you sort of use the model's own knowledge about its class conditioning in order to do this guidance. And this is a bit weird, and I feel like this shouldn't really work. And I feel the fact that this works appears to be a little bit of just a hint that our current models aren't making use of the data fully, because we have to do these tricks at inference time. So it's more pointing towards us not really being the masters of these technologies yet, rather than this being some sort of an intrinsically good thing to do. But essentially what we want to do is, during training, we train these class conditional things, right? We train, let's produce the noise that was added to xt in the last step, conditioned on y. And y here could be a class label, y could be the input text, y could be, pretty much any conditioning information. And then we also, alongside that, sometimes we don't provide that label at all. We don't provide the label, which essentially means that we are training an unconditional generator. So we just simply forget the fact that we have labels. We simply train an image generation model unconditional. Okay? So we just give the model XT. We ask, here is just some image without description, without nothing. What was the noise added to this image? And now at inference, so we just train the model in both ways. During training, we sometimes just leave away the label. This could be beneficial, as this part, in fact, would be the opportunity to bring more data into the picture, right? Let's say I have only part of my data is labeled and part of my data is unlabeled. We could actually, in here, bring in the unlabeled data and therefore get more data into the system than we usually had. But given that they probably have enough data with their giant image caption dataset here, by the way, it's the same dataset they used for DALL-E. Given that, it's probably they just leave away the text at during training for some of the, they say right here, with an all label with a fixed probability during training. Now, during inference, you can do something with that. What you can do during inference, you can say, well, if I am in the situation where I have an image and a label, and I ask my model to generate the noise, what I can do is I can do a little bit like the same thing I did with the clip guiding. So here I let my model predict the unnoised version, but I also push it into the direction that clip tells me would be a good image. Right? So it's two things. This is, given the image, what would be the unnoisy or the less noisy version, and this one would be, well, in general, which image would be sort of appropriate for this piece of text. You mix the two objectives. This is very much the same. So if you unpack this, you can see that this right here unconditionally asks, given this image, which is the less noisy version of the image, or give me the noise that was added to the image. And then you push it into this direction right here. And you can see this is the difference between the noise that the model predicts unconditionally and the noise that the model predicts conditioned on the label. So this is a direction. This direction points very much into the direction of the noise that was specifically added to the label, right? So it's the difference between the conditional and unconditional prediction. We add that to the predicted noise right here. So the model predicts, okay, this is the noise that was added, and the conditional model predicts this one, and then we simply push the prediction into this direction. You can see right here, there's a scalar s involved. S obviously must be larger than 1, because if s is smaller, like this is what we would predict usually, the conditional one. So now, if s is larger than 1, we're going to predict something more up here. And notice the difference. If we didn't have this, we would simply predict this point right here. We wouldn't know which direction was a better direction. Because we also have the unconditional point right here, we can clearly say that this direction is probably the direction that goes into the direction of the conditioning information. So we can choose to sort of overdo it. Again, I think that's kind of a trick around the fact that we don't know how to handle the information very well quite yet. I'm not sure, but it seems like you wouldn't even have to do this necessarily. What you could also do, if you want to go further, you could take sort of inspiration from the contrastive learning communities and maybe do you could also replace this part and this part, by the way. So these parts you could replace sort of by an expectation of these noises over some labels y hat or y prime. So which means you could just sample some other text or some other conditioning information randomly and get an expectation. You could also do hard negative sampling. So you could take labels that are fairly close, or you could take labels that are kind of confusing and try to differentiate yourself. So there's a lot of possibilities here. I can see that, but still it feels like a bit of a trick. Yeah, so good. That's what they do. They do clip guidance. So they do this classifier-free guidance, which turns out to be the better variant. And they also do the clip guidance, which is what we discussed before, except with clip, you can see they've just replaced the gradient of a classifier with the gradient of the clip model. The clip model is simply an inner product between an embedding of the image and embedding of the text. And they say the reason probably that the classifier-free guidance works better is because the clip mod, sort of the diffusion models, what they do is they find like adversarial examples to clip and not necessarily good pictures. Now, I don't know if the classifier-free guidance would also be something that could replace sort of the current notebooks that are flying around where clip is used, clip-guided diffusion and VQGAN plus clip. But I'm not sure, because the VQGAN, it seems, already restricts the space of images, such that it's not that easy to find adversarial examples, because it always has to go through the vector quantization. Okay, that's the model. Like, the model is nothing else. It's a diffusion model, all right? This has existed before. It is conditioned on conditioning information. The diffusion model itself is conditioned, in this case on text that goes through a transformer encoder, which is the blue thing right here. These embeddings are then sort of concatenated into the process of this diffusion model. The diffusion model is a model that for one of these steps tries to predict the reverse. It's the same model for each step. It just gets as an additional conditioning information which step it's currently trying to reconstruct. It always reconstructs the noise that was added. Training data generation is pretty easy. You simply add noise to an image and then you add a bit more, and then the difference between that is the target to predict. Then at inference time they also do this guided diffusion. Right? That's either going to be achieved by clip, and the disadvantage of that is that you have to have an additional classifier like clip. Not only that, but in fact, the classifier has also have to been trained on noisy images because otherwise noisy images are going to be out of its distribution. So they do in fact train noised clip versions. The disadvantage, as I said, is you need this additional model that's trained on noisy data. The advantage is that you get to bring additional information here. You get to essentially potentially even bring additional data sets that was used to train these other classifiers. You can use multiple classifiers, whatever. They also do classifier-free guidance. These two things, they don't use them together, clip guidance and classifier-free. They use them either or. The classifier-free guidance is more like a hack where you, alongside the conditional denoising, train an unconditional denoising. So you train the model also to sometimes not be conditioned, and then you push it into the direction away from the unconditioned towards the conditioned and beyond to make it extra conditioned, I guess. The disadvantage here is that it seems like a hack. The advantage is that there's potential maybe to do some hard negative sampling, and also it doesn't require an extra model on the side. And also in the unconditional training, you might bring in additional data that has no label. So training happens, it's a 3.5 billion parameter text conditional diffusion model at 64 by 64 resolution. This is way smaller than DALL-E, by the way, and this is cool. And a 1.5 billion parameter text conditional upsampling diffusion model to increase the resolution. So it's a two-stage process. The diffusion model itself is at a 64 by 64 resolution, and then they have an upsampling model. So it's also text conditional, but it is so this is purely a diffusion upsampling model. It's very much the same principle, except that it now doesn't go from noisy image, or sorry, from pure noise to image. It goes from low resolution image to high resolution image. And alongside of that, they train a noised clip model, which is the classifier that they're going to need to do guidance. Well, they describe here a little bit of the architectures. We're not super interested, at least I'm not super interested in the architectures. They're way big models. As I said, they release the small models. They don't release the big models. And they explicitly train for inpainting, even though you could do it with diffusion models without training. But they say if you train it, it behaves a bit better. So during training, they would sort of mask out random parts of the images and then use diffusion to reconstruct those. And yeah, the results are the results that we've already seen. These are pretty interesting. They do studies with it. So they do studies on these data sets. So as they increase the guidance scales, the guidance scales are like the only handle they have at inference time. That to trade off diversity and sort of adherence to the data set. And it turns out that the classifier-free guidance, as you can see right here, is behaving better. This be the frontier right here. These always trade off two different metrics in the MS COCO dataset here: precision recall, here inception score, and FID. And you can see the only time the clip guidance is better than classifier-free guidance is when you directly look at the clip score. That's why they say probably the clip guidance simply finds adversarial examples towards clip. They also let humans rate the pictures in terms of photorealism and caption similarity, and you can see that the classifier-free guidance wins both times. And that's pretty much it. They show some failure cases, which I also find pretty interesting. So an illustration of a cat that has 8 legs is not a thing. Bicycle that has continuous tracks instead of wheels. It seemed a bit like DALL-E as a model was more sort of sensitive, or was more respondent to text itself, so to the prompt. Whereas here it seems it's more like generating realistic images that has some sort of the words. So the words kind of match with the text. A mouse hunting a lion, not happening. Also a car with triangular wheels, also not happening, as you can see. I myself have tried the small model a little bit, and you can see, you can try it yourself. I'll put a link up. There is a Gradio space by the user Valhalla. Thanks a lot for creating that. So here is balloon race. You can see that works pretty well. A drawing of a tiny house, that's also okay. A hidden treasure on a tropical island. I mean, it's a tropical island, right? But yeah, all the elephants had left a long time ago. Now only a few vultures remain, and it's just kind of a bunch of elephants. So, well, the elephants are kind of walking away a little bit, right? Yeah. Attention is all you need, obviously. Oddly Russian vibes from this picture. And this one is glory to the party. And I guess party is just sort of equated with birthday cake or so. So the sort of text sensitivity of this model might not be as good, but there might be opportunity to fiddle here. The samples as such, they look pretty cool. It's also not clear how much of a difference this is between the small model and the large model, or how much effort into diffusion is put. They also say they release the model they release is sort of a model on a filtered version of a data set, and the filtered version removes, for example, removes hate symbols and anything to do with people. So they say it's not as easy to generate deepfakes. Yeah. And where was... Yeah, I think the coolest one is where you can do this interactively. That is a pretty cool one. I want to look at lastly, where is, sorry for the scrolling around, safety consideration. So there's so, like, they say, as a result, releasing our model without safeguards would significantly reduce skills required to create convincing disinformation or deepfakes. And they say they only release the small model. They say this somewhere. Where is it? Well, in any case, they only release a small model, but I just want everyone to remember GPT-2. And it was exactly the same. And to my knowledge, there's not, the world is not in chaos right now because people have used GPT-2, which is sort of public by now and can be easily trained by anyone. The world is not in chaos because people have access to GPT-2. It's not the case. And I don't know why they do it, because for PR reasons or because they want to kind of sell the larger model, sell access to it. I mean, that's all fine, but don't tell me this is safety considerations. And yeah, the fact is, people are going to create deepfakes in the future. It's going to be easier, but it's kind of, the answer is not to not release the models and techniques. The answer is to educate people that, hey, look, not everything you see on a picture, especially if it looks like it's upsampled from 64 by 64, not everything you see on there might be entirely real, right? Things can be altered, things can be photoshopped, things can be created like this. It's the same as people have learned that not everything that's written in an email is true, and people will simply have to adapt. That's going to be the only way. Not giving people access to these things seems to be kind of futile. But as I said, I don't believe for a second that actual safety considerations were the reason for this. In any case, let me know what you think, and that was it from me. Try out the model, and maybe you'll find something cool. Bye-bye.